Welcome. So I've been a little bit off on these. So let's get caught up. This week I wanted to talk about more about natural numbers and specifically talk about a couple lemmas that are here. So I want to give this proof, which is the proof that the only natural number that divides one is one. And the way you prove that, because we're gonna actually use this, we're gonna do some problems that are more proofs by contradiction. This one is I'm gonna let m be a natural number that divides one. So by definition, we know that m is greater than or equal to 1 because 1 is the smallest positive integer. So because it is and so this inequality right here, this inequality is all about the fact that it's a natural number. So that inequality gives me that this, so it has to be at least 1. However, since m divides 1, then there is another natural number such that mk equals 1. Well, since k is greater than or equal to 1 and m, if I multiply both sides by m, we get mk is greater than m, but mk is 1, which means that 1 is less than or equal to m. So I just swapped out right here for a 1 because mk is equal to 1, and I had this inequality, which gave me this, because again, k is a natural number, which gave me this inequality, so we're here. But that means that m is between, over here, notice it's bigger than 1, and right here, it's less than 1. So between these two inequalities, the only way m is less than or equal to 1 and greater than or equal to 1 is that if it's equal to 1. And so this is one of those things, this is not a proof by contradiction, it's direct proof, because all I did was say, okay, let's let m be a natural number that divides it. And then it simply restricted it to the point where that was the only possible answer. This actually, ironically, sometimes is the best way to attack these problems, is to give them a direct proof, not a proof by contradiction. So let's look at a different one. This is one that I want you to prove. Let p be a prime number and let n be any integer. If p divides n, then p does not divide n plus 1. And hint, to prove this, think about something I asked you to do on the discussion boards last week. It might imply this very idea right here. Here is another one that I want you to work on. And this one is one that you can do, but it's a little bit more technical. And I'll give you the beginning of it. We want to prove that there are infinitely many primes. So I'll give you a couple of hints right now for this one to help you out. First, I would do a proof by contradiction. What do I mean by that? Well, so you were going to assume, the reason being, to prove that there's infinitely many of something is really, really hard. But if I prove that, so if a proof by contradiction would be, suppose there are finite prime numbers. All right, what do I mean by that? So that means I can actually make a list of them. I can literally make a list of prime 1, prime 2, up to prime k. This could be all the prime numbers. This literally could be the set of all the prime numbers. That's what a finite set would give us. I will tell you also, one of the things you might think about is, all right, so you have a finite set, then something you might want to use is the previous lemma. So getting rid of this and going back, this lemma right here, how does those prime numbers, if they all divide n, how does it affect n plus 1? So you might want to consider all those prime numbers something that involves all those prime numbers. And then how can I use that lemma? I'm short of telling you, it's really, really a classic one. And think about this for a second. All you need to do is create some, if there's finitely many prime, show there's some other number that's bigger that's not divisible by any of those primes, and therefore it is a prime number. And that would break your prime numbers. You're being finite. All right. So those are your two things I want you to do, is I want you to work on this lemma which again should feel very similar based on what we did on the discussion board. It's a side topic just recently. And then this, which actually used that lemma. And you might, and a proof by contradiction. All right, that's your task. Good luck. Let me know what questions you got.